We imagine the internet as an invisible abstraction, but dive beneath the floorboards of any data center and you find a massive mechanical reality. Every moment spent online depends on a tangible mechanical connection to the physical world. The global internet is simply a worldwide collection of interconnected local networks, cooperating to exchange data over actual hardware. Every device we use, from the laptop on your desk to the smartphone in your pocket, right down to smart cars and hospital heart monitors, relies entirely on this continuous chain of physical equipment to function. To truly understand how networks communicate, IT professionals have to look past the user interface and strip away the software completely. We have to examine the raw base data being transmitted, the physical media carrying it, and the real-world obstacles that slow it down. Troubleshooting the internet requires treating it as a rigid mechanical system, governed by the laws of physics, rather than a theoretical void. At the very bottom of this mechanical system is the absolute base unit of digital logic, the binary digit, or bit. A bit is not a conceptual number. It is a precise measurement of one of two discrete physical states, an electrical charge that is either on or off, a 1 or a 0. When you type a character, computers use standard binary codes, like ASCII, to group these individual bits into 8-bit sequences called bytes. If we break those inputs apart, a capital A becomes the exact sequence 01000001, and a 9 becomes 00111101. This diagram illustrates what happens next. To cross a network, bits must be converted into physical signals. The first method relies on copper wire, translating data into pulses of electricity sent as jagged signals from machine to machine. The second method requires fiber optic cable, converting electrical signals into pulses of light traveling down a central optical tube. Finally, devices can translate data into radio waves, broadcasting the signal directly through the air. A single message will rarely stay in one format. As it travels from source to destination, the signal is converted multiple times to cross different types of media. No matter how sophisticated a software application looks on your screen, all global data transmission strips down to these three physical phenomena. Those physical connections scale outward, starting with the simplest configurations. A small office or home office network, a SOHO, might wire together just a laptop, a printer, and a single router. Contrast that with the massive infrastructure of a corporate campus. Here, physical lines branch out, connecting thousands of individual hosts into a single unified grid. This graphic demonstrates scaling up further. The World Wide Web is millions of local grids wired together globally, and the endpoints of this network have evolved beyond desktop computers, extending directly to the mobile devices in our hands. Today, a smartwatch tracking your pulse or smart glasses projecting a display push physical data onto the network. Inside the home, everyday refrigerators, smart TVs, and gaming consoles are wired to centralized servers. Outside, industrial RFID tags, agricultural sensors in the soil, and mechanical actuators exchange data to automate real-world logistics. The global internet consists of the total physical infrastructure built to route electronic signals between this endless variety of edge devices worldwide. Getting signals across the planet requires capacity. Bandwidth is the theoretical maximum amount of data a medium can carry in a given time frame. This capacity is strictly limited by the physical properties of the medium and the governing laws of physics. We measure this theoretical pipeline in bits per second, scaling from a few thousand kilobits all the way up to billions of gigabits per second. But theoretical capacity is rarely what you experience. The actual, measured transfer of bits over a specific period is called throughput. Throughput is always lower than bandwidth. Different data types and file sizes ensure the physical flow is never perfectly smooth. The main culprit is latency. Every time a packet hits a physical barrier, like a router, it takes time to process, causing a traffic jam. Throughput is reduced even further because your network pipe isn't just carrying your files. A portion of that bandwidth is always consumed by network control messages and error correction traffic just to keep the system running. This creates a hard physical limit. In any multi-segment network, total throughput can never be faster than the slowest single link in the entire path. High bandwidth provides raw capacity, but network engineers must calculate for latency and physical bottlenecks to find the actual speed a user will experience. Let's trace a single piece of data through this physical gauntlet. Imagine an agricultural soil moisture sensor. The dirt dries out, drops below an acceptable level, and triggers an alert. Immediately, the sensor's processor translates that environmental change into a binary state, a bit. For its first physical hop, the device broadcasts that bit as a radio wave, sending it to a local monitoring station. The station receives the wave, translates it into an electrical pulse, and pushes it down a copper wire toward the local internet service provider. At the ISP, that electrical signal is converted into a pulse of light, injected into a high-bandwidth fiber optic backbone to instantly cross the country. The fiber provides enormous capacity, but the final throughput is ultimately dictated by the processing delays of the routers it hits before logging into a centralized database. Network engineering involves mastering the physical journey of binary states across varied media to bridge our digital and physical worlds.
The reason I'm presenting this to the students is because I want you guys to start thinking bigger. I want you to start thinking about this career stuff now. With the onslaught of hearing a lot about AI, I want you to get really deep into understanding your career path.
In this particular lab, which is titled, of course, 1.5.7 Packet Tracer Network Representation, this particular lab is to teach you everything you need to know about packet tracers and how to use it and use the devices within here. Now, it's not going to give you everything like I just said. It's just going to give you the scope of how deep you can really learn how to use this particular device to better understand networks. So let's take a deep dive into it and just start breaking down some of the things. Now, I want you to understand all clients have full connectivity to the server. As you can see here, if you look at them, they pretty much are connected to the server. And I have it right here on this screen. One of the things I like to do when I'm working on a lab, I like to either have two monitors or I like to just split it in half so I can see both of the devices. Most of you have learned how to do this and you do it. So that's kudos to you. So I just want you to know this is a better way of representing things. And you're going to get a chance to see me blow stuff up and shrink stuff down. And when I say blow up, I don't mean literally blow it up. I mean just make it bigger. So now this lab here has a network. This is not a real network. This is just something that's showing you how a network will look. So I don't want you to walk away thinking, oh, this is how everything is really. Networks are truly more complex and complicated networks out there. I mean, and if I can say that again, networks are really, really complicated. But this is a snapshot of what you will have to do. So for the sake of frame diversity, the environment is not entirely realistic, okay? If you think about it, for instance, net and PAT overload on both networks. So let's go to the objectives. One of the things I also want to point out is, which I teach you in the class, is once you put your mouse pointer over anything, it can tell you the connections that you have in there on these devices. So make sure you do that just to see what type of connections. Like on this particular cell phone right here, and I'm gonna blow that up so you can see it better. On this particular cell phone, you can see if I come here and put my mouse pointer over here, it's gonna show you the gateway, the DNS server. It's going to show you the IP address that's being issued out to that cell phone. Or so you can see it's a lot of things going on in this particular network. So it says here, over here on the objectives, what is the objective? Remember, everything has a topology, everything has an objective, and we want to make sure we understand what we're doing in order to be able to do it. And you want to remember this. So our particular objective in this particular lab, or excuse me, packet tracer, the network model in this activity incorporates many of the technologies that you will master in your CCNA studies. It represents a simplified version of how small or to medium-sized business networks might look. So let's get clarity here. This is just giving you a bird's eye view of how a network will function. So just imagine, you just want to see what's going on within it. So feel free to explore the network at your own pace to learn as much as you possibly can. And if you complete the lab, go back and do it again, just to make sure now that you have some knowledge, you can better do things. Okay, just a side note, in this particular lab, it says it is not important that you understand everything you see and do in this activity. So feel free to explore. Don't get caught up with saying, I want to make sure I understand it. Sometimes I have students that try to be so perfect in this that they tend to lose the point of it. The point of it is for exploration purposes. Let's say that again. Exploration purposes. It is to give you a bird's eye view of things that you can do in here. So don't get stuck here, which you haven't. Now, identifying common components of a network as represented in the packet tracer. This is step one. So you just want to be able to take a look at the different components in here. So it says list intermediate device categories. How many intermediate devices do you see in here? Well, let's shrink the screen down and take a look. So as you can see right here, you have a plethora of intermediate devices in here. Just take a look at them. So if I wanted to know, I have intermediate devices. I have what? I have routers. I can see 1, 2, 3 routers. I have switches. I have 1, 2, 3, 4, 5 switches. I have modems in there. I have wireless devices in here. I have LAN in here. So you see, you have a multitude of intermediate devices within your network. It's going to be up to you to demonstrate that you have that, okay? Now, also, it wants to know, without entering into the internet cloud or intranet cloud, how many icons in this topology represent endpoint devices. So you should be able to count out how many endpoint devices. Now I'm only going to count a few of them, and I'm going to leave it up to you, which you already did, to tell me how many actual devices is. You may or may not have done this lab, but if you did, you probably already told me. But if you haven't, how many devices? Now remember, I am talking about the endpoint devices, okay? Okay, so not going into these intermediate or the cloud to count them. How many devices in here? Endpoint devices. Now I'm not going to tell you the exact number, but let's say I go 1, 2, 3, 4, 5, 6. Okay, that's 6 I counted. I know that it's more than 6 in here. My expectation is that you will tell me the exact number. Okay, let's move forward with that. So you know what endpoint devices are. The next one asks this, without count of, so let's say we here it says we did the intermediate devices, we did the endpoint devices. Now it says here, without counting the 2 clouds, how many icons in the topology ref intermediate devices? Now I pretty much already told you that, but I'm not going to tell you the full number of the intermediate devices. What I'm going to do is count a few of them, but you got to tell me exactly how many in there. So if I look at an intermediate device, I go 1, 2, 3, and I'm going to leave it there because I want you to tell me the total number. So find out what an intermediate device is and tell me how many in there. The next one says how many end devices are not. Now remember, how many end devices are not desktop computers? Well, this looks like an end device right here. I'm gonna blow that up for you so you can see it. So this looks like an end device to me, but it's not a computer, so I would count that. This looks like an end device to me, and it's not a computer, I count that. Even this looks like an end device, and it's a computer, but the question said this. The question said, how many are not desktops? Okay, so this is a laptop, it's not a desktop. So I can tell you right now, that's 1, that's 2, that's 3. What about this here? Can that be considered a end device? That's not a desktop. So I'm gonna let you tell me the exact number. I know the exact number, but I want you to do some work. And then the next question in this section, to close out this section, says how many different types of media connections are used in this network? Now, I can see multiple media connections, and I can come down here and click on the connections to help me out. So I see this connection right here. If I come down here and move it over, that says serial. So I see a serial connection right there. That's 1. Then also I see these black boards, cables. What are they? I can come down here and move over and see that that's a copper straight through. As you can see, represented right down here, copper straight through. And I see them now. Now I'm gonna stop there. I just gave you 2 of them, but I know it's more. Okay, it's a lot more. So as your professor, I'm expecting you to tell me all of the end devices. Now there's one in here that will trick you up. So make sure you pay attention to your lessons. Remember the lecture I told you about. Okay, if you hear me drinking some, I'm drinking my coffee. You know this is morning time. Coffee, baby, coffee. Okay, let's move on. Okay, step 2 is just basically explain the purpose of the devices. So now this is when you get the chance to share your knowledge with me. This first question says, in Packet Tracer, only the server PT device can act as a server. Desktop or laptop PCs cannot act as servers. Based on your studies so far, explain the client-server model. You should be able to explain the client-server model to any IT manager. In our modern networks, a host can act as a client, a server, or both. Software installed on the host determines the role it plays on a network. You should be able to point that out. So if you think about it, if I put software on a desktop computer that's network software, I can turn that desktop computer into a server. Servers are hosts that have software installed that enables them to provide information and services. So just remember that I can take this PC and turn it into a server. I wouldn't do that. That wouldn't be wise. That would not be smart, but I can. But this is what a server is. A server issues out special software to the other devices so it can give them the services that they need. That's what I should. Clients are hosts that have software installed that enables them to request and display information obtained from the server. So these clients are reaching to this server. So that's one of the questions that I expect you to know. You should be able to go into any interview and explain what a server can do. Okay. So it says here, list at least 2 functions of intermediate devices. Maintain information about what pathways exist through the network and internetwork. You should be able to explain that to me. So it's multiple things you should be able to tell me, but I just need you to list 2 of them. Remember, just 2. Okay, and the next question is, list at least 2 criteria choosing the network media type. So why would you choose specific network media type? List at least 2 reasons why you would do that. So 1, you could say the distance the media can successfully carry a signal. That's important. Let's say these 2 branch offices. This is the central office and this is the branch office. Well, what media would you choose to go from point A to point B? Okay. The environment in which the media is to be installed. What the environment. So why would I use fiber optics in this when I know that it'd be better to use coaxial or straight through? So just make sure you understand 2 definite reasons why you would do this. Remember, all this playing out for a reason so you can understand how these networks function and what's the purpose and the decisions why we make decisions to choose the different devices and medias that we use. The system checking out.